Hello everyone and welcome back to Causality with Boris, all broadcast from SobolevSpaces. In this video, I talk about an algorithm for effect identification by conditioning. What's an algorithm? Well, it's a set of rules. Make sure you watch examples. I'll share practical tips for applying the backdoor criterion to various causal diagrams. After that, please compare your notes with takeaways at the end. I prepared a PDF with the algorithm for this video. To receive it, click on the link in the description and it'll be in your inbox. The backdoor criterion gives us a general guidance, but it doesn't describe steps to find out if the effect is identifiable. We do it right now. But first, let's recall how paths get blocked. A path between treatment and outcome is blocked by collider or by conditioning on a common cause. Now we're ready to put together rules for establishing if conditioning on some variables can identify the treatment effect. First rule, list all backdoor paths between treatment and outcome. They start with an arrow pointing to treatment. Second rule, check if all backdoor paths are unconditionally blocked. If the answer is yes, then the treatment effect is identifiable. If the answer is no, then next rule, check if conditioning on non-descendants of treatment will block the open paths. If the answer is no, then the treatment effect is not identifiable, at least not by the backdoor criterion. If it's yes, then move to the next rule. Check if conditioning opens non-causal paths. If it doesn't, then the treatment effect is identifiable. If it does, next rule, check if conditioning on other variables can block them. If not, then the effect is not identifiable. Remember that variable may be a collider on one path and a common cause on another. So conditioning on that variable may eliminate common cause bias, but it may induce stratum selection bias. Not conditioning on the variable would lead to common cause bias, but it would eliminate stratum selection bias. Be sure to apply one last rule. Check if the conditioning variables or their descendants lie on the causal path. If the answer is no, the effect is identifiable. Otherwise, it is not. Now I'll walk you through examples. They show you how to answer our question, is the effect identifiable by conditioning? Some instructions before we start. Each diagram will have treatment and outcome nodes. A path between them could be causal or non-causal. Variables denoted by capital U are not observed. When you find an effect is identifiable, write conditioning variables down. And if it's not identifiable, then list non-causal paths between treatment and outcome that you cannot block. As a warming up, let's consider this graph. There is only one backdoor path between T and Y. It starts with an arrow pointing to T and goes to U1, to A, to B, and to Y. Is it unconditionally blocked? No, it's not. There is no collider. Is not B a collider? It's not. So this backdoor path is open. Our next step. Can we block it by conditioning on non-descendants of T? The path is open because node U1 is a common cause. It'd be natural to condition on U1. However, it's not observable. We can't condition on it. We can observe two other nodes on this path, A and B. B is a descendant of T on a causal path, so we rule out conditioning on it to comply with the backdoor criterion. It looks like node A is our only choice for conditioning. It lies on the open non-causal path, and it's not a descendant of node T. So the answer is yes, the effect of T on Y is identifiable by conditioning on node A. Let's imagine how conditioning on a node would look graphically. There would be no arrows pointing to or from the node, and the following graph shows conditioning on A. We removed all its arrows. As a result, all non-causal paths disappear. That leaves only causal paths between t and y. Let's add two arrows to the previous diagram, from u1 to e and from u2 to y. First, list all backdoor paths between t and y. They start with an arrow pointing to t, and there are three, from t to u1 to a to b and y, that's 1, t to u1 to e and y, that's 2, and then t to u1 to e to u2 and y, and that's 3. Let's inspect these three paths. Look for the presence of head-to-head arrows. There are none. All backdoor paths are open. Can we block them by conditioning? Let's look at non-descendants of treatment. Conditioning on A blocks path 1. Conditioning on E blocks two paths, path 2 and path 3. Therefore, we should condition on A and E. It'll block all backdoor paths. Again, don't include node B into the conditioning set. It's a descendant of T on a causal path. So, is the effect identifiable? The answer is yes. Let's take a look at this diagram. It shows the result of such conditioning. Notice the arrows pointing to and from nodes A and E. They're all gone. No non-causal paths are left, and that path producing a variation between t and y. In the previous examples, we had first one conditioning variable, then two. So what does conditioning mean in practical terms? It means stratification. Combinations of values of E and A determine a disjoint strata. For instance, if both variables are binary, that is, they are either 0 or 1, then we end up with 4 strata. Here is our next diagram. It shows a graph with blocked backdoor paths. Can you find it? Pause the video and give it a try. Was it the path that goes through Z3, Z1 and Z2? Yes, that's the one. Collider Z3 blocks it. Two arrows are pointing to it. It's a common effect of U and Z1. Still, there is another backdoor path, from T to U to Z3 and Y. I've reviewed many articles, and researchers often argue to condition on Z3. They say it's a cause of Y. We can apply a graphical criterion now to see if it's a good idea. The diagram shows that conditioning on Z3 will block path 2, but it will also open path 1, and we can't condition on Z3 anyways. It's a descendant of T on a causal path. So the answer is no. The treatment effect is not identifiable, at least not by conditioning on variables lying on backdoor paths. Is effect identifiable by conditioning? The answer depends on the DAG structure, but also on the set of conditioning variables, and more than one set may satisfy the backdoor criterion. Some observations from previous examples. First, to identify the treatment effect, we don't need to condition on all immediate causes of treatment or all immediate causes of the outcome. Please send me your thoughts on this. Next, we always had a single treatment and a single outcome, but the backdoor criterion works for multiple treatments and outcomes. It even works for treatments spread in time. Then we always had a complete diagram, DAG that fully represents relationships among factors at play. What if the DAG is not fully known? Control for all pretreatment variables. That's what conventional practice suggests. The kitchen sink approach. Here is a better idea. If there are observed pretreatment variables and they meet the adjustment criterion, then it's sufficient to condition on causes of treatment or outcome, whether they are immediate or distant causes. That's the recommendation of 2011 paper by van der Wiede and Spitzer. The backdoor criterion, such a helpful tool. It gives us conditioning variables, and they permit the identification of the total treatment effect, all through simple conditioning. Before it, we used conditioning implicitly through stratification. Now we know for sure. The algorithm is based on the premise that DAG is true. Yet the power of DAGs is often in revealing which identification strategies do not work. To show that identification by conditioning isn't achievable, you don't need additional assumptions to DAG. If it doesn't work in a simple DAG, it won't work in a DAG with more errors, although it may work with additional nodes. You just watched the application of the backdoor criterion. The main message of this video: there is an algorithm to find out if the treatment effect is identifiable in a given causal diagram. Let's recap. First, list all paths that start with an arrow pointing to treatment. If they are unconditionally blocked, then the treatment effect is identifiable. If not, then check if you can block them by conditioning on non-descendants of treatment. If not, then the effect is not identifiable. If you can block them, then check again if conditioning opens non-causal paths. If it doesn't, the treatment effect is identifiable. Don't miss this idea. To identify the treatment effect, we don't need to condition on all immediate causes of treatment or on all immediate causes of the outcome. Keep on watching.